Hi, hello, welcome to section 4 of this chapter. So in this section, we are going to discuss valence bond theory. So valence bond theory is one of the oldest explanations of why bond forms, and it is still relevant in some aspects, but now we have more information on bonding. So we have a couple more theories that we discuss. So in this section, a short section, I will explain what is the valence bond theory is and how it supports the formation of the bond through its explanation. And in the next couple sections, like in section 7.5 and 7.6, I'm going to talk about the advanced version of bonding theory, which is hybridization theory, which I kind of, a little bit denounce what we just learn here. That's how science works, right? You got new information, and if something is wrong in the past, you denounce the previous one, not to say the bad things about it. It is good when it is first implemented, but now we got more information that is more accurate to what we currently know, right? So spend a little bit less time on it, and because there's some issues with it, minute issues, but most of the information is still correct. So how rest of this chapter goes is you introduce bonding theory here, and you discuss advanced bonding theories in section 7.5 and 7.6 and 7.7. That gets a little bit more intense there. So let's see how valence bond theory works. It is basically happens when atoms share electrons to form bond by overlapping their orbitals. And how do they do that is by when atoms ready to form bonds, they use their atomic orbitals and they overlap one over another to facilitate the sharing of electrons between those orbitals. And it happens only when those electrons in those orbitals are oppositely signed. Oppositely charged or signed is also a word that I can use here. So what is the advantage of forming this bond over staying as single electrons for these atoms is formation of a bond will result in a lower potential energy. I have a diagram to show you in the next slide. What I mean is, again, I'm going to repeat this. Formation of a bond between two atoms results in lower potential energy for the molecule. What it means is it has low energy, which means it is more stable in chemistry, having low potential energy. So as a result, the atoms in a molecule are more stable than individual atoms of the same type. That's why atoms love to form bonds, because it gives them stability. Let's see here, we are discussing the example of what is the stability in compared to single hydrogen atoms versus hydrogen atoms that made bond by overlapping their atomic orbitals. Here, if you can see, here is the approximate energy for the single hydrogen atoms that were not bonded together. In comparison to that, the hydrogen atoms that were bonded together in this case has the negative 436 kilojoules per mole of potential energy. What does that mean is you need to apply 436 kilojoules of moles of energy on it to separate these two, just to have the single hydrogen atoms back, which means hydrogen molecule as HH is 436 kilojoules per moles of energy more stable than single hydrogen atom. Again, it is possible because they were sharing electrons, they form the bond, and bond only forms when the potential energy of a system is lower than the individual atoms. So as a result, valence bond theory comments that atoms would love to form bonds because it results in overall low potential energy when they form bonds. Here is another example of a atom trying to form a bond. When you have fluorine atoms, if you look at the valence electrons for fluorine, it ends with 2s2 2p5. And if you want to check on the orbital electron configuration, you can see that single electron there. So when one fluorine atom wanted to bond with another fluorine atom, it uses one single electron of one orbital and overlap with the another single atom of another orbital. As a result, they form bond. So one, another electron, they must be opposite sign. So as a result, they form bond by overlapping each one of their orbitals like that. That's how bond forms. Here is another example here, and we just, as a matter of fact, couple examples. So bond can happen between any different number of atoms. Let's say if you're trying to see how a bond between HF can happen, it happens when hydrogen atom uses its 1s orbital single electron to react with the 2p5 single electron of fluorine, and when they overlap one with another, the bond forms. As a result, you form bond like that. And is the bond stable? Let's look. When HF bond is formed, it has the bond energy of 568, which means it is highly stable, even more stable than H2 and F2 alone. So as a result, HF bond is formed because instead of staying as individual hydrogen fluorine atoms, HF as a bond connected to by overlapping hydrogen 1s orbital with fluorine 2p5 orbital, it's shown to be more stable as in the form of molecule. All right, let's work on this last problem in this section. Hydrogen selenide is a foul-smelling gas that can cause eye and respiratory tract inflammation. The HSE-H bond angle in H2SE is approximately 90 degrees. Use the valence bond theory to describe the bonding in this molecule. Okay, what is a selenide? Where does selenide found? Selenide should be found in group 6, so it should have the electronic configuration of 4s2 3d10 4p4. So you only worry about last empty valence electrons 4p4. So 4p4, if you try to draw the orbital diagram of it, it has those two single electrons. So what it means is it can make two single bonds with another elements. As a result, it bonds with hydrogen atom, two hydrogen atoms with each one having 1s and 1s orbital to form SEH bond. So why it has this 90 degrees angle approximately is because the p orbitals of these are one is perpendicular to another. As a result, they have the bond angle between those two as 90 degrees. That's how they have the approximately 90 degrees bond angle between H and H in H2SE. That's all for this section, and I'll see you in section 5 of this chapter soon.